Alright, so welcome back again, and this is the Chipmaster, and in this video series I will be repairing a MacBook, and it's written on it here, says no power. As you can see, it says no power there, right? And this is what is written on it, no power. Alright, so I'm gonna plug in the charger now to see what's taking place on the DC power supply here and on the amp meter here. All right. Okay, so this is the A2338. All right, it's a M1 series. First generation of the M1. As you can see, it's an A2338 series there. MacBook Pro. So I'm plugging in the charger now. Type C power supply. Alright, so as you can see, it's taking 5 volts and it's not boosting to 19 volts or 20 volts, you can call it. So it's stock current there, and the current, as you can see, is 210 milliamp there, and it's not boosting. Okay, so I'm going to take it apart now to see what's going on inside. Alright, so I have an NBA match to go and watch in a few. It's the Boston Celtics versus the Pistons, I think. I need to watch that match. This is the part that I don't like. Let's see if I can get inside that small groove here. Alright, got that edge there. Alright, just sending a text message there. Alright, so I'm just inspecting here on the on this side of the board for any corrosion or any liquid intake. Alright, so looking around, so before I take out the motherboard on this side of the board to see if I see anything obvious, and I don't see anything obvious, so everything should be fine. Looking good so far. Alright, so we can continue with the disassembly process. Oops, I didn't pull the clip. Okay. This one has never been pulled before. I am the first person taking apart this laptop. All the clips are tight. You can feel the difference in the removing of the flex ribbons. See? Alright, so all the flex ribbons are now disconnected. Now removing the main screws. All right. Alright, so the board is out. Alright, so let me go on to the next side of the board for inspection. Alright, so on this power delivery chip side there is good. Alright, down to the charging section here. That's good. No liquid intake, any burn. The board is clean. Not even a speck of dust is on the board. All clean and nice. Alright, so the board is good in terms of its appearance. Alright, so first I'm going to check resistances. First I'm going to check PP, but oh god, this glare. Let me turn off this additional light. Alright, so first of all, I'm going to check the PP bus, the main power rail, at the fuse. Oops. And it's good. I'm getting 400 and 450, so it's good. There's no short there on PP bus. Alright, so I'm gonna check 1.2 PP 1.2 volt S2, and that's good. That's a crucial signal. Also, I'm gonna check at 3.8 volts. That's under this plastic here. So this is our main standby, which is equivalent to PP 3.42 on the older boards. So this is PP 3.8 volts to give power to the auxiliary. This is the main PMU IC, and under here we have our auxiliary IC, PMU IC, and that's also good. Alright, no short on that side, 3.8 volts. Alright, so I'm going to get the DC jack. So all the main power rails are intact, there's no short. So I'm just taking out the DC jack now so I can do some hot checking. I have a feeling that this board is going to turn on for some reason, I don't know why. Alright, so the DC jack is now screwed down. So I am plugging in the charger now. Before, let me check around. Let's go under the microscope. Alright, so under the microscope for PP3V3, which is coming from these two chips, the power delivery chips here. So on the meter, let me go and zoom in some more closely. Oh, I see why. Alright, so now I'm checking these capacitors here, and that's good. That one is good, all good. The other one, which is here, that's good, that's good, that's good. So why it's not turning on though? No short. So I'm plugging in the charger now, and I get no lights. It's not boosting. As you can see under the microscope here, I'm still getting 5 volts and it's not boosting. Alright, so I'm gonna check for the 3 volts that it's coming from. First of all, let me check around the Wi-Fi area here. It's normally tend to have a shorted cap or a short on this rail. Alright. Alright, that's good. And that's good. So there's no short. Oh, sorry, I did hold on the camera. Alright, no short there. Alright, no short there. No short there. So PP3V3, that's the S0 state rail. That's no short there as well. Alright. So I bet one of these voltages are fluctuating. So let me check 1.2 volt S2, which is here. This coil, if it's fluctuating, go to the voltage gear, and I'm not getting it. No voltage at this point. 0.2 volts, as you can see. Let's see if we're getting 3.8 volts at any of these coils here. Yes, I'm getting 3.8 volts, as you can see. 3.8 volts is there, right? All of them, all 3 coils are in parallel, and I get 3.8 volts, so that is good. So the PMU IC should be getting power. Once the PMU IC gets its all working condition, supply, reset and clock, then it will immediately send an initialization to the M1 CPU, right, to start to boost, because the T2 chip, right, the T2 chip, as we all know, it's inside of the M1 CPU. Right, so the T2 chip is inside of the M1 CPU. Right, so we are getting 3.8 volts here. After the 3.8 volts is generated, right, the main auxiliary PMU IC will start to get its working condition, supply, reset and clock. Then it will send the power to turn on and to start initialize the M1 CPU, right? After the M1 CPU is initialized, all working conditions are intact, then it will start read its RAM chip, and this is the EEPROM chip here. Right, so this is the EEPROM chip for the M1. It will read and configure its GPIO pins and the watchdog, right? So once the watchdog PMU pole reset is okay, then it will start to talk to the power delivery chips to boost the voltage to the designated voltage, right? So this is how it works. So once you plug in the charger, the laptop, the board will learn the capabilities of the charger, such as the power supply, the amount of current that it can generate. Then it will send a packet ready, or a packet request signal to the charger, and then the charger will receive that command and then accept the ready command, and then start to initiate the correct voltage and current for the device that is going to be powering. I wonder if you get what I'm trying to say right here. Right, so this is how this mechanism works. So this is the M1 CPU. The M1 CPU has the T2 chip inside, right? The T2, which is embedded inside of the M1 chip. So the serial number is no longer stored inside of the EEPROM chip here, right? On the T2 models, the serial numbers is stored on the T2 ROM. So this ROM doesn't store the serial number on the M1 series anymore, right? It is stored inside of the M1 CPU. Okay. Oh, sorry, let me. Have a slack connection here. All right, so as you can see, I get 3.8 volts, which is going to turn on the PMU IC. I should be getting 12 volts here. Excellent, I'm getting 12 volts, right? But it's not boosting, right? So the M1 ROM, is it getting 1.8 volts? Is that pin 1? Yes. So first of all, I'm not getting any voltage here at this coil. Alright, so I'm going to head over to the schematic to see what's going on the board circuit wise, so I can have a proper analysis of what's going on the board. Alright, so I'm on the Shinjijao database, so I'm going to type in the board number here. So it's 820 hyphen 02020 02020. Alright, there we go. So I'm opening the schematic, and I will also open the board view. Alright, so I'm just waiting for it to be opened. Alright, there we go. And the board view. Alright, I'll use that one. Okay. Alright, so this is the side of the board that we are focusing on. So here, as you can see, it's on this section here, right? This is our 3.3 volts, 3.8 volts. As you can see, PP 3.8 volts always on, right? And this coil is PP is 3.3 volt S2, right? PP 3.3 volt S2 voltage, as I said before. So I'm not getting this working condition. So let's find out why it's not generating. So here is the circuit. As you can see here, we have this chip, which is UC710. Right, and this is a typical PWM circuit. As you can see, we have a switch, and we have a coil, we have a filter capacitor, as you can see, which is a tantalum capacitor, right? See, polytant, and we have some regular ceramic capacitors, 10 microfarad, and this is 150 microfarad, and the feedback, as you can see, feedback, right? So the feedback circuit, which is going back to the feedback pin of this chip, right? So first of all, we need to check the input, which is a supply, which is coming from V in, as you can see here, V in, and we are coming from all the way up here, and it is PP bus underscore A on, right, underscore 3V3 S2 underscore V in underscore sensing. right? So we need to check here if we're getting 12 volts here, as it says PP bus. So PP bus means the main common point rail, which is 12 volts, and we're going to check at pin number 1. All right, so pin number 1. Let me go under the microscope. All right, let's get in the lights. All right, so I'm plugging in the power now. All right, so pin number 1. All right, good. So let me all right, so pin number 1. Which is coming through this resistor here. So I'm getting 12 volts, as you can see there. So I'm getting 12 volts. So it's the input, which is 12 volts, as you can see, which is right here at this capacitor. Sorry, 12 volts is there. 12.34 volts. All right, so that's good. Next. We have the enable. All right, and it's coming through the 0 ohm resistor to pin number 8. So let's see where this is coming from. And it's coming from U8100, and this is most likely our PMU IC, right? So if to confirm it, we go back to the board view, and U8100, this is our U7700, and this is the second auxiliary chip. This is the auxiliary chip, sorry, and this is the main PMU IC, U8100. So it is coming from this chip. So this chip needs a set of working conditions, right? Supply, reset, and clock. Once supply, reset, and clock is coming okay, right? Once it gets that all working conditions, supply, reset, and clock, then it will start to work. So that enable signal, which is here, as you can see, and it's coming through a 0 ohm resistor. This is a 0 ohm resistor, right? And it's coming from directly from the PMU IC here, as you can see. So I'm gonna go back under the schematic, let's go back to the microscope. All right, so the enable signal, which is coming from pin number 8. Let me all right, so yes, it's coming from pin number 8. Just need to confirm something on the board view here. All right, so pin number 8. Which is here. And I'm not getting any voltage whatsoever. All right, no voltage. This is a 0 ohm resistor. And there's no voltage coming from it. So our PMU IC is not sending any voltage whatsoever. See? And there's no short. I already checked here for shorting, and there's no short there. Right, so I'm checking again. See, I'm getting 386, no short there on PP3V3S2. So we are getting 3.8 volts. So I'm going to check around the PMU IC to see if I get any abnormal reading. Alright, so that coil there, so that's good. Alright, so I'm checking around the coil. Alright, so that's good. Alright. Alright, so that's good there. No short. That's also good. Alright, here. Alright, so that's good. This coil, that's good, no short. Alright, that's good. Alright, that's good around that coil there. You have to check all of them. That's good. That's good. That's a ground, sorry. That's good. That's good. So I need to check if, so first of all, I need to check if the 3.8 volts is coming to the PMU IC. Alright, so the PMU IC has a main coil, so I'm going to go back to the schematic. So this is the PMU IC U8100. Alright, so this has how many pages? So we have 6 pages, a total of 6 parts. So this is 5 of 6. This one is 4 of 6. Alright, let's go up. These are the ground pins. This is 6 of 6. These are ground for the buck converters. Each buck section has a ground for the lower MOSFET that is inside of it switching. And these are the buck converters. As you can see, we have buck 3 feedback, buck 3 ground feedback, right? Buck 7 output, right? Output 0, 1, so 1, 2, 3 outputs, and these are in parallel, as you can see. All of them are in parallel. Alright, so let's go up. Alright, so we have VDD main, as you can see here. 1.2 volt PP 1.25 S2, which is a linear voltage which is coming out. VDD IO. These are all linear supplies. And here we have the main power supply, which is the master PMU box. So PP 3.8 volts, this is the main power supply, as you can see. And it's coming to VDD buck. These are the main buck to power all the buck converters that are inside of the PMU IC here. And this is 1 of 6. This is the main first page. And we have here the RTC, right? This is for the RTC section. So it's going to turn on the RTC section inside of the buck converter, inside of the PMU IC. All right. Alright, so there's no more pages up there. Alright, so these are some other power supplies. PP 1.8 volt S2, PP VDD CPU SRAM awake. and these are all coming out of the PMU IC. Some are going back to power other modules inside of the PMU IC. So we have PP 1.8 volt awake, PP 1.2 volts awake IO, and these are the input 1.8 volt S2, 1.25 volt S2 from box. So it is powering back itself. So the power is going back into the chip itself to power other modules inside. Alright, so that's the main power supply, PP 3.8 volts, and that is already coming to our PMU IC. So our PMU IC needs power, right? So we get the power. So I don't have to check here because it's already getting PP 3.8 volts by default. So once it gets that voltage, then we have to look for the linear voltages that are released from this chip. Okay, so we need to check first for, let me go back to the schematic. I was on break. So we need to check here first. We need to check all these rails if we are getting the linear voltages. So once we get the main power supply, the PMU IC itself has to release LDO voltages. Every PWM IC, right, every typical PWM IC needs to release a linear voltage so that voltage can go back into the chip as a reference and also a working voltage, right? So this is supply, right? So we have VDD, VDD main, VDD LDO, as you can see. So all the LDOs have to be powered, right? LDO stands for low drop out. So we get the box power supply VDD, then we get the VDD LDO power supply, right? And then the chip itself will output LDOs, right? Sensing, right? This part is labeled as sense, this part is labeled as voltage inputs, and this is buck outputs, right? So we need to check these supplies, 1.2 volt, all the S2 voltages. So PP 1.2 volts, PP 1.25 volt S2, PP 1.8 volt S2, right? And we're going to check, as you can see, where these are coming from. As you can see, it's a lot of pages. I normally start from the bottom, going on, then go all the way up. All right, these are not relevant, not relevant. As you can see, PP 1.2 volt S2. So these voltages, all right, so here we are at a critical section here. So the next, this is buck 13. All right, let's go up. There's some capacitors there. PP 1.2 volt S2, and this is a connection here. This has the UART debug. This is a debug section, SOC, all right, DFU MUX selection, all right. So these are for debug, which is used by Apple most times, as you can see. And it has UART debug, so this is used by the factory from Apple. All right, 1.2 volt S2 is coming to this N-channel MOSFET. As you can see, this is a MOSFET that is used as a Zener diode, which is acting as a protection. So this MOSFET has protections in them, right? So you can see all these are used for the LEDs, right? And it is controlled by PP3.8 always on, which is coming to this light emitting diode to turn on this LED, as you can see. And it's coming to the drain of this MOSFET, which is controlled by IDP power enable. This is also coming from the PMU IC, right? This is for the DFU button there. First DFU mode, supplying 1.8 volts to here will automatically send the laptop into DFU mode for Apple configurator or for other troubleshooting debugging purposes, right? So this 1.2 volt S2 is critical, 1.85 LDO, and this is coming through the EMC filter, which is for the touch ID. Right, this is going to the power button connection. Right, this voltage won't be present unless the linear voltage is released from the PMU IC. IDP SPI interrupt. I think this is for the trackpad level shifter. If this is faulty, the trackpad won't work. As you can see, SPI trackpad underscore TPad underscore initialization underscore connection. So this is a key signal. If this is a gate. As you can see, we have A, Y, right, not connected ground, right. We have supply A and Y. So this is any input comes in, and the same comes out, right. So this is a gate, similar to a regular. We can call it a shifter. So it's a level shifter. Yes. And this is for the trackpad. As I said before, any of these signals are not working, trackpad and keyboard won't work, or keyboard only work but the trackpad doesn't work. Alright, we have a pull up here, no stuff. Alright, that is not used. As you see, it's not installed. No stuff indicates that the component is not there. And there's a lot of places that this is going. Alright, keyboard backlight PWM level shifter. We have A and B ground. Right, what comes in, what comes out. Right, same way in, same way out. So no voltage drop, no voltage loss, no current loss. Right, backlight PWM. And this is where this is another pin that is, we have GPIO. So this is read by an EEPROM chip. This is not important at the moment. So this 1.2 volt S2, we need to find where it is coming from exactly, right? This is the CD32 chip, as you can see, CD32. So I'm going to check here at this capacitor, VDD IO at CF502. And that's right there. So I'm going to check. All right, so that's on UF 500. Right there. So this cap here is, let's see if we're getting 1.2 volt S2 there. Oh, let me go on voltage. No voltage is there. Oh, sorry, I'm in front of the camera. So I'm not getting any voltage there, as you can see at that capacitor. All right, 1.2 volts. Let me check there for shorting. If you're not getting voltage, always check for shorting. All right, and that's good. No shorting there. So that 1.2 volt rail is okay. All right, so let me go back to the schematic. So I need to go back now to measure the other LDOs. So I need to go back to the page that I was coming from. This is the M1 chip. Right, so we have here 1.2 volt S2 debug, and that's for the SoC, which is our M1 most likely, PMU reset. So this is the PMU reset for this is the main reset signal for the M1 chip. Right, so our M1 chip needs a reset signal. So this 1.2 volts is critical to pull up this reset signal for the cold reset, right? PMU cold reset, which is the main reset signal, right? And we have the watchdog will be initialized, right? SOC watchdog. So we need these two signals in order for the M1 CPU to work, but we're not there as yet, so we need to see the other rails, right? So I'm at the end of this part, so let me go back down here. I need to find back my original page where I copied this signal from. Let me go up. Let me pause. Okay, so now our next one, which is 1.8 volt PP 1.8 volt S2, and this is going to a lot of places, as you can see. All right, so because of time, I will have to go through them at a faster pace. As you can see, we have VDD PP 1.8 volt S2 switch, VDD1, right? Trackpad VR voltage regulator, USB 3v3. So this is a alias. All these are aliases. All right, for the master PMU box section there, and these are aliases. All these section here is for alias. So let me skip till I reach, here we go now. So here we are at the actual part to start to see where it's going. So that's a capacitor there, filter capacitor. We have SOC VDD1. It's coming to that connector there, that debug connector, coming to the LEDs as usual, and so forth and there. So as you can see, it's going to that level shifter there for the SPI interrupt for the trackpad as usual. Right, this is a digital mic flex section there. So many places this signal is going. So we have so many places we can check for this particular voltage. Let me see if I can pick. All right, going up, and it should be also going to our power delivery chip as well. This chip is, this is a USB. Let me see what chip is this, and this is PP3v3 underscore switch sense. Level shifters, USB. This is a touchpad. This is a USB interface for interacting with other devices. As you can see, it carries an I2C line, clock and data. That's not important at the moment. Here we have, that's not important, the same thing. That's a level shifter there, another shifter. So this voltage is going to so many places. Alright, so here's another chip which is coming to our CD3217. So we can check here like we checked before. And this is the cap that we're going to check, CF503. Right, and that's going to the same cap tip that we went. So let's go back over to the schematic, to the camera. All right, so that's located here, that cap there. Let's check for shorting. Let's check if we're getting voltage. All right. All right, so, and I'm not getting any voltage there. I'm getting some voltage here. I'm getting 0.6 volts. I'm getting some volts there, but it's incorrect. It should be 1.8 volts. So let's check if we're getting any short in there. No short. No short there. And that's all good. But it's incorrect. It's incorrect. So let me pause. Okay, so after checking thoroughly through the schematic, right, I had to pause the video as the video will be very long. I went through each section, each power rail, and I found PP 5 volt boost, which is a boost section. This cap was cracked here and shorted, as you can see here. Right, that capacitor there was cracked, as you can see right here. I haven't removed it yet, but upon checking I saw I found a short, and I spotted it with my eyes under the microscope. So that's right here, and that's signal, which is, as you can see on the cap here, which is a PP 5 volt boost LQ master PMU, which is also connected to PP 5 volt boost underscore LQ Vout PMU, right? And this is for the internal buck converter, which is releasing 5 volts, right? And this was shorted, this capacitor here, and that's how I found the short. So I'm going to remove it now. Sometimes these shorts send a feedback to the PMU IC, can also damage the PMU IC. Oh, sorry. Alright, so one of the leg there, the cap is removed. So let me check here. Alright, so it's restored to 435. Let me check for the PMU. Very good. So this coil is very important here. It's acts as a filter to filter out any clutter and to protect the PMU IC there. Right? So this is restored, and these coils easily burn. If any spike should induce on the line, remember, these coils basically blocks high frequency and passes low frequency. This is why they are called low filters. Filters, which is basically used to filter out, right, any spike, and filters it with the help of the filter capacitors. Right, so a coil basically passes low frequency and blocks high frequency. Right, so I'm going to plug in the charger now. Alright, and it's still not boosting. Ha ha ha. Okay guys, so I had to pause the video because I was going near close to an hour. So what I discovered, so after lifting this capacitor here, As you can see, I lifted the cap here, right? It still didn't boost, nothing changed, right? So I know normally the coil that is supplying that rail, which is this coil, I had to replace it. As you can see, it's now replaced. Go back. Right, so it was replaced, right? And this is sending that 3.8 volts to the PMU, which is for one of the buck converters to turn on, as I said, the LDO and the buck converters. So we see these small capacitors here. Most of these small capacitors are LDO supplies, and these are PWM buck converters, right? All these coils here. So this is the main power supply. All these are supplies. Some come before pressing the switch, some comes after pressing the switch, right? So please bear that in mind. So this is the coil, which is the main VDD main, right? VDD buck supply, which is supplying 3.8 volts. So when I plug in the charger now, as you can see, so I have to skip out that part because the video will be long, too long, and I don't want that. So I plug in the charger and I measure here. Right, so as you can see right here, I get 3.8 volts. So the coil was broken inside of the coil. One of the legs, it melted and break, so it wasn't making contact. So as you can see right here, right, 3.8 volts. Right, and the next side we have 3.8 volts. So on one side I was getting 3.8 volts, on the other side I was getting 0.6 volts, 2.8 volts, sorry. So I realized that something is wrong. So so that was a short there. So I'm going to replace this capacitor, very important. Right, so I'm waiting for the iron to get hot. Alright, so I'm now tilling that pad there, and I'm going to put a new cap there. Alright, so it's all tinned and ready. This is a common fault. So this is a signature fault. Luckily it didn't burn the PMU IC. Alright, I've seen where this line shorted and also burned the coil and end up burning the PMU IC due to high current, because this circuit is constantly working, so the coil is constantly filtering, and then eventually it will break. So you have to change that coil. That coil is weak from the factory, so you have to use a coil with a larger microhenry. So that microhenry, which is going to withstand the amount of current that is going to be calculated from the front end and the back end. So this is why there is a current sensing resistor. So this is why there is current sensing resistors, as you can see here, right? So wherever you see current sensing resistors like these, so here's one, right? Let me go back some more. Right, so we have current sensing resistor here, we have one here, and you have another here. Whenever you see that, you know that there's a large amount of current that is distributed on that supply, because they're all in parallel. So what will happen is that this the PWM chip that is controlling these three phases needs to know how much current is produced at this coil, so it doesn't run hot. These coils run too hot, and these MOSFET will burn because they are switching at a very high frequency. So this is why they put these current sensing resistors at the back end of the coil. As you can see, it's at the rear stage, right? Each of these rear stage of the coil has a current sensing resistor to sense the amount of current, so it can adjust the switching of these MOSFETs so they don't burn. So this is why on most of the gaming machines they put a thermal pad on these, because the chip needs to compensate for the temperature of these 3 phases. So each phase has a set of current which is shared, and then that shared current is sent back to the PWM IC, which is this IC, right? And it is also monitoring the current and the temperature. So we have impedance compensation, current compensation, and temperature compensation. So those are the 3 types of compensation that is found on a typical PWM circuit with a large amount of current, such as the CPU power supply on ordinary computers, right? So please bear that in mind. So I will now get the cap, and I will put a new cap here. So this is why that circuit is burning, because it's not sensing the amount of current, so it's not adjusting. So this is an error that Apple did when creating the circuit, because this circuit is sending 3.8 volts, but at the same time the PMU IC is not compensating for that amount of current, and that overcurrent will come and hit the PMU IC and causing it to break. Luckily the coil disconnected itself so that it end up burning the PMU IC. So as I said before, I've seen many times where this coil break and end up burning the PMU IC. So this is a very poor design that is done by them. So what they should have done is put a current sensing resistor, right, also here. But as I said, this is a blind man, so this doesn't know what is going on this side. Let me zoom out. So this chip is a blind man. Yeah, it is a blind man, so it doesn't know what is going on here. So it always going to be talking through the current sensing resistor, through the PMU IC, to the PWM chip to adjust the output current. But at the same time, this doesn't communicate with the PMU IC, with this chip, so that it can tell it to adjust its output current, right? And so it can limit the amount of current so that it doesn't send too much current to the PWM IC, to PMU IC, and then it can protect it. But at the same time, it cannot talk to the PWM chip here. So this is a typical poor design that is done by Apple here, right? By not allowing this chip to talk to this chip through an SVID or some form of a data line or I2C line, right? So I will get the cap. All right, so I now have the new capacitor, set of capacitor. I will now install to the designated spot here. There we go. Add in some flux and there we go. All right, so let me just firm a firm joint. So I'll now clean this section now with some 99.9. There's an extra bulb there. Let me just remove that. Alright, oops. The solder catches this cap here. Just want to remove it, make it nice and shiny and neat. Alright, there we go. So Okay, so I'm allowing the board to cool, and then I will connect the charger now. Alright, so as you can see, it has now boosted to 19 volts, and the current there is 115 milliamp thereabout. So it's boosting and the current is jumping. As you can see, it's now 100, 300, 500 milliamp. Alright, and it's there 200 and 200 milliamp, 100 milliamp thereabout. So I think it should be all good now. Alright, okay, so that was a done job. So I'm going to put this unit back together now, right, because of time. So I'm going to cut out all that part. I'm over basically an hour and 8 minutes now in the video. So I will put this unit back together and get back to you. Okay, so now we're going to connect the battery terminals. Alright, just making sure all connections are intact. Making sure everything is connected. Alright, all is well. Alright. Alright, so shall we? Alright, it seems the batteries are dead. So I'll just connect the charger. The battery is not having any power. There we go. So we have Chime and we have Apple. There we go. So we have display there. It's a bit dark. Alright, so as you can see, the display is there. And that's a done job. And the battery is now charging. As you can see, we are getting fast charge, 2.5 amp on the DC power supply. So as you can see, I'm getting fast charge in there as well. So that's a done job. So that is why the screen got dim, because the battery wasn't sensing. So it has battery saving options turned on. So now it should be able, after the battery reaches pre-charge, it's in trickle charge now. Once it reaches the designated amount of voltage for the threshold for the battery, then the brightness will be adjusted back to its original PWM voltage from the factory, or based on what the user set. Alright, so I hope you enjoyed the video, and I hope you like and subscribe, and I'll see you again when I will repair something for you in the next video. Okay then, bye.